Okay, good morning and welcome to the lectures on Hamilton-Jacobi equations. And in the last lecture, we were discussing some calculus of variations and the corresponding Euler-Lagrange equation. So let me briefly recall what we were doing in the last lecture. So we are trying to consider more general Lagrangians of the form LXQ, where L is from Rn cross Rn to Rn. And then you have your similar AT. It's a set of all admissible trajectories, and we have these notations introduced, dxl and dql. So these are all vectors because x is a vector, q is a vector, and then L is called the Lagrangian, and this is a jw is the corresponding functional, and we want to minimize w, so we want to derive necessary conditions, that is for optimality. And that means if w bar is an optimal solution, that is minimal solution to that one, so what's the corresponding necessary conditions? And this is not something new. The only thing is that what we are going to do it in infinite dimensional. We know in finite dimension if x naught minimizes a functional, and then if x naught such an x naught exists, and if f is differentiable, so you need a notion of differentiability in the infinite dimensional Banach spaces or Hilbert spaces, and then f prime of x naught equal to 0, which is a necessary condition. So by solving f prime of x naught, you could possibly find all the minimizing point if x is. Okay, so we start with the same thing here. So you want to derive Euler-Lagrange equations. That's what we are going to do it today. As I said, these are some necessary conditions. Okay. So you assume W star is a minimal solution. W bar is a minimal solution, minimizing the functional given above, minimal solution. So we are going to, of course, W satisfies the condition W0 is equal to Y and W at T is equal to X. Okay, so we are going to do that one. That means this implies your J of W bar is less than or equal to J of W for all W in AT. And of course, W bar is also in AT. Okay. So that's the meaning of a minimal solution. So I choose special test functions to derive necessary condition. So let tau be any real number. And you choose a V, not in AT, choose V such that V at 0 is equal to 0, that's equal to V at T. So it's a trivial boundary conditions. Therefore, if I choose W is equal to W bar plus tau V, this is and V is smooth. V is C2 function. Okay, so V is also smooth, but V doesn't contribute any boundary condition, so it will retain the same boundary condition. So this is equal to AT. Okay, so I fix T for the time and later I vary. So fix T V as well. Fix V. W bar is already chosen, which is fixed. So fix V, and then that implies J of W bar is less than or equal to J of this W, that's nothing but W bar plus tau of V. This is true for all tau in real number. Okay, so that means now you will try to do a differentiation process. So I consider one variable function in tau variable function f tau. It's a variable function in thing because W bar and things are fixed. J of W bar plus tau V. I fix that one, and what is my F0? Therefore, F0 is equal to J of W bar less than or equal to J of F tau, because by the previous thing this is true for all tau. That implies tau equal to 0 is a minimum point, and one-dimensional minimum point, and that implies if f is differentiable, of course we will show that f is differentiable, that and if f is differentiable, then your f prime of 0 equal to 0. So I want to compute, I will do something in between. So we want to compute f prime of tau. Okay, so to compute f prime of tau, you write down this definition and you do the integration under the integral sign. So what is your f of tau? So d by d tau of f of tau is equal to this one, right? J of w bar plus tau, that's by definition. So recall your JW definition. JW definition is this one. So you have to write the correct argument properly. So d by d tau of f tau is equal to integral 0 to t L of, okay, w bar plus tau v, w bar prime plus tau v prime. That's the definition of S. Everything acts on S, so it will be acting on S. So ds. That's what this is, just by definition, d by d tau of that. So you do the integration under the integral sign. So if you do this integration under, so this is a vector. These are all vectors. So you have all the variable. So if you want, later I will give you first time let me give you a summation notation, I equal to 1 to n. So you want to differentiate with respect to the first argument. When you differentiate with respect to the first argument, you will get LXI, the first term LXP, LXQ it is. So LXI into the same argument. So I will not write repeatedly right here. So this right here. So that's the argument. And then you have to differentiate this term. You have to differentiate this with respect to tau, and that will give you V. Okay, Vi prime. The ith component with respect to tau, if you differentiate, you will get your Vi. And then you differentiate with respect to the second variable, that will be LQI, and put the same thing here also. Into differentiate the second argument with respect to tau, that will give you Vi prime. Everything with respect to S, ds. So this is the summation. You'll get it. Now look at the second term. So you can do Vi satisfies the zero boundary condition. So integrate by parts. So you have to do an integration by parts here. Integration by parts. And your Vi 0 and so the Vi t is equal to 0. So and let me also write so this derivative Vi prime will come to LQI. So the derivative Vi prime will come, the derivative will become, so you can write down, and let me do a combined notation. So this will become 0 to t, and I will remove summation, and I will write dx of L, and then integration by parts. So there will be a negative sign coming here. So there will be d by ds. Okay, so there will be a d by ds of this Vi prime coming. So d by ds of integration coming here, you will have dq of L. Of course, evaluated at that variable. Okay, so again there will be exactly that component. This component will be coming. Okay, L coming here, and then these are all with the dot product, the derivative Vi. So it will be dot product with V. Okay, ds. That's the thing. So in particular, so let me use the same color. So in particular, I can compute my f prime of 0. F prime of 0, because it's an argument in tau equal to 0, f prime of this comes, arguments are w bar plus tau v. So if you want to compute at 0, you put tau equal to 0, so you get w bar prime, everything in S. So you will get 0 to t, okay, dx of L minus, so d by ds of dq of L evaluated at w bar of S, w bar prime of S. Okay, that's argument dot product V with ds. Okay, and this is true for all V equal to 0, for all V smooth. Okay, since it's true for all V smooth, therefore since there's some integral action on V is 0, so f prime of 0 equal to 0 implies this term equal to 0 for all V smooth with 0 boundary condition, and that implies the integrand is 0. So that implies you can change the sign if you want. D by d, let me write it in a standard format. Changing this dq of L minus dx of L is, of course this is all evaluated at the so this is an evaluated at the optimal solution. So w bar prime, this is equal to 0, and this is the Euler Lagrange equation. This is the Euler Lagrange equation. So as I say that, so if w bar is an optimal solution, then it satisfies. This is a system of n system. N equations are the system of second order equations. Second order ODEs. Okay. So we will eventually write this system n second order equations into a 2n first order system later, using what is called the Hamiltonian. So defining Hamiltonian involves some work which we may not do it today, but we will before going further. So what is the theorem basically? So let me complete the theorem format. Theorem, what we have done. Okay, so let L be as above, and W bar is an optimal solution, minimizing solution when I write optimal solution. That is, J of W bar is equal to minimum of J of W in AT, then W bar satisfies the system, satisfies the ODE system star. What is star? This is your star. Okay, system star, that is d by ds. Okay, maybe we'll put it whatever way you like it, otherwise don't get confused. If you, both are same, minus here plus here, both are same because it's a equality equal to 0. So let me write it, minus d by ds of dq of L minus dx, this is which you can solve it. Okay, dx of L, of course you evaluate at the optimal solution. W bar of S, W bar of prime of S equal to 0. Okay, so that's the Euler-Lagrange equation, how you will derive. So let me make a remark. So I am going to give some examples. Let me make a remark before going to examples, which is exactly like one dimension. For example, in one dimension, if x0 is a minimizing f of x in an interval, then you know that if f is differentiable, f prime of x0 equal to 0, but f prime of x0 equal to 0 need not be a minimizer. So similarly, if W bar is a minimizer, it satisfies the second order ODE system, but that doesn't mean that the second order ODE system can have solutions but need not be a minimizer. So any solution, so that's why any solution of Euler-Lagrange system star is called a critical point, is called a exactly like called a critical point of f. Okay, so the minimizer, therefore minimizer is a critical point, but the converse is not. But converse need not be true. Okay, so this is similar, and then we call it, so basically you have derived something, your f prime of tau here. So you see you are derived an f prime of tau here, and so we can compute in particular, you calculate f prime of 0, this one. That's what and that's true for every v. So in formally we can write, those who have studied, so formally you can write f prime of 0 is nothing but j prime of W bar, because bar evaluated at v, and this j prime of W is known as Fresher derivative. So you say you have a concept of derivative known as Fresher derivative. See, this is in infinite dimension. So you are basically looking at this thing by fixing at v. Okay, so f prime of 0 is basically is equal to j prime of W, and then f prime of v is 0 because f is depends on v. Okay, and then f prime of 0 equal to 0 is equivalent to j prime of W bar equal to, therefore f prime of 0 equal to 0. You see, this f is depends on v, please keep it in mind. So that should be a dependence on v, that's the v coming here in j prime of W, equivalent to j prime of W bar v equal to 0 for all v. That's we also write it as the Fresher derivative is 0. That's the meaning of a functional. The Fresher derivative is going to be a functional. Alright, so with this we will connect, as I said, the system of 2n equations, n equations in second order, we will convert it into a first order system. Okay, and that first order system using the Hamiltonian, and that involves little more work. So before that, let me go to some examples. So we'll start with some interesting examples, and in this class some of the details you have to work it out. So I will not be giving. The first example 1 is from classical mechanics, the Newtonian mechanics. So what we are doing is something more than the Newton's law of motion. Okay, you have to understand that. So all the things available for Newtonian mechanics may not be available. So the Newtonian theory of about the world view is a specific choice of L. Okay, so let me write. In this case, I will tell you the problem which you know. In this case, your Lx cube is basically m by 2. M is a constant, mod q square minus vq. Okay, vx. Or let me write it as vx. So this is, in this case, this will become the kinetic energy. You see, I told you in this case q has to be x prime eventually, and that's nothing but velocity. So this is the kinetic energy. And this is your potential. So this is a difference in kinetic and potential energy. And there is, what Newton's law of basically tells you that there is a least action principle. That's what you do. Least action principle. So the Newtonian mechanics follows this. Newton. So if you want, you should read some classical mechanics. Newton least action principle, you minimize the action integral. So you have your m by 2 t L of x of s, x prime of s. Okay, so since I am using w, let me use w only. So I'll use w prime of s. You can use any notation you like. So Lx is that one. So you see, and how do you get Newton's mechanics? So Newton's basically want to study the motion of a particle. Under the influence of a force, and in special cases forces F, and under like conservative forces, this is given in a special system or conservative system, and special case is a conservative system where F is given by a potential. F is equal to some d phi x, and phi is called the potential. That is what the physics basically in the Newtonian thing. Phi is called potential, and that's the thing we have used it. So you see, so you eventually you want to find the least action, and this is called it is called action integral. So we will use the same terminologies, action integral. Okay, we are going to use the same terminology. So this integral, and so Newtonian mechanics is nothing but a very, very special case of a Lagrangian. So what we are doing is in the present study is more general Lagrangian. As I said, everything will not be that easy, especially construction of a Hamiltonian, because there is in the classical mechanics there is a Hamiltonian which turned out to be the total energy. That means sum of kinetic and potential energy, and you can go from one system to Lagrangian formalism to Hamiltonian formalism, which I will indicate later in the next class. But in this case, so you are a simple exercise, you can prove it. It's not an exercise, but you can easily do it. While you compute a Euler-Lagrange equation, which you already know that Euler-Lagrange equation, and this turned out to be what you get it is m into w bar double prime of s, and is equal to f of w bar of s, and that's nothing but your d phi of w bar of s. You see, this is nothing but your second law of motion. So this is nothing but this is second law of motion, right? Newton's second law of motion. Okay, you see. So what we are doing is a kind of generalization of that. This you just write down your Euler-Lagrange equation, you will get it. Second law. So second law of motion is a necessary condition for your action integral to have a minimum. Okay, that's what the study. So let me go to another example. So I want to give two more examples before finishing the example 2. There I will not write down the equations. So it's your job to write down the Euler-Lagrange equations. I'll just leave that one. This is what is called a Brachistochrone problem, which you probably, many of you are already familiar. Brachistochrone problem. This problem was introduced by Johann and Bernoulli in the 1600s or something like that. Okay, I don't know exactly when it is introduced. Maybe. Okay, anyway, that's immaterial for the time being. John Bernoulli and then many people like Newton, Leibniz are all worked to solve these problems. So you have to understand that the early days, 1500s and 1600s, the idea, normally people proposes problems to the scientific community and you look for solutions. And later people try to give a general theory, making mathematics is little bit of an abstract subject. Okay, and even the Daniel Bernoulli and other people worked on this. And the more interesting thing is that this uses, the initial proof uses Snell's law of refraction. Snell's law of refraction. You see how physics is concerned. So it's not, so what we are given is a much more general theory than what you know it. Okay, so it uses that kind of Snell's law of refraction of light. Okay, so you have this thing. So what does this mean actually? Brachos means, I will tell you, Brachos means shortest. This is a Greek word, shortest in Greek. And Chrone means time. So the shortest time. When I explain, you will understand the meaning of. Okay. You will understand shortest. So you want to study. So let me explain the problem first. So you have a 2 points. You can think it as a vertical plane. Think it as a vertical plane. Okay. I will put the coordinate later, A, and this is a point B. Okay. So there is a bead. So there is a curve here. And bead is traveling. So I will put the coordinate system in this way. Okay. So this is the point A0 if you want it. And this is the point corresponding to B0. Okay, so you are traveling from this point, so A, B0, so this will be some B, some other number. At B, you can put it some n point in the y coordinate, say YF final coordinate if you want it. So a bead is traveling. So so this curve we call it y of x. Okay, so this is your x and this is your y. So let me quickly write down. A bead is traveling along this curve y, and a bead is traveling along the curve y under the only influence of gravity, under the no influence of gravity. No other force is acting. Okay, so only it is moving towards. So what is the problem? Find the curve y. Find the curve y, so that the bead takes the shortest time, not shortest length. Shortest length is the straight line. Okay, shortest time to reach B from A. Okay, so that's the problem. So you want to find the problem is to compute the time. So we want to understand what is the computation of the time. So what is the physics? The physics is the energy is conserved. So you just compute your energy. Energy is conserved. Okay. So you write down the energy. So let V, so you compute the position. So you compute any point here. So for any point x here. So this is your y of x, the distance, and let the velocity be v. So okay, let the v is the equal to y prime is the velocity, be the velocity. So the energy, initially the total energy is, so and y is in the negative direction. So to understand, initially total energy is 0 because there is no kinetic energy and it is moving under the influence of the gravity. So at the point A, there is no energy. Initially energy is equal to 0. Therefore, at any time, any x, okay, any x, the total energy is 0. So you just write down the total energy. Because once it moves, it picks up the energy is equal to 0. So you have your kinetic energy. Kinetic energy is my2, and then you write down the potential energy mghy. This is equal to 0. Because the minus sign comes because it's moving downward. We have written the coordinate in that direction. That's the reason, that one. So from here, you can compute V. Compute a relation between V. You get V is equal to so you normalize it. It is not compulsory, but you can normalize because for your computations it's easy. You take mass 1 and g equal to half. This is not necessary, I'm telling you, and this is not, but otherwise you have to keep tracking of this one, and then you will get your y is equal to v is equal to square root of y in that case. Otherwise there will be a parameter sitting here. And then what is the functional? So you compute the length of the, so if you want to understand the time taken, so the total time taken to move from A to B is you compute the length of the curve. So it is from A to B, you compute the length of the curve, y prime of s square, and then divide by the velocity, basically. Yes. ds. Okay. So this is your j of, I used y here, so this is your curve y. So what is your problem? So there your problem, find this is the time taken. So the problem, find y bar. So you see y bar such that your j of y bar is equal to minimum of j over y, all that smooth curves of j of y. And what is your here? What is your LXQ? Your LXQ is nothing but square root of 1 plus mod q square by, it's a one dimension thing, and your square root of mod x. Okay. The distance y is taken as to be positive direction. So you have your x. So you see. So the exercise, I will leave it as an exercise. I will just tell one more problem before I say exercise. Find Euler-Lagrange equations. And once you solve this one, I will not do all this work. You can refer some books or something like that. That's not the main aim, because we have other thing. To solve the solution, y is a part of a cycloid. Is a part of a cycloid. So you understand what is a cycloid and all that. The parametric form of a cycloid is, which I will, the parametric form of a cycloid. So I am writing in a parametric form. Your x is that some a plus c into t minus sine t and c into 1 minus. You can do all these are all exercises. So maybe we will provide you exercises later. So you first write down the second order equation, solve it. When you solve, you get this equation solution. It's a part of a cycloid. Cycloid is obtained by rolling a wheel. It will form a curve. So it will be part of a cycloid. Okay. So let me present you one more example before I conclude. Example. Again, I will just write down the example, but you do this, the further things as the time is up. So we will, example 3. This is what is called a catenary. So let me, again, this is introduced by Bernoulli, and then many other people worked on this one. So typically you have a chain. Catena means chain. Catena means chain. Okay, so let me describe you a problem. So you have, let me also introduce the coordinate here. So you have 2 points and you have A and B, and you have a chain at A if you want it, chain, and chain is hanging. Yeah. Okay. Okay, chain is hanging here. So what is the shape of the chain? The problem is, what is the shape of the chain? Of course, chain is too big. It's possible that chain will come and stay here. So we are avoiding that. Also you can solve it, but we want a, okay, so chain doesn't looks like a chain. So typically people will think that it will be a part of a parabola and things like that, but that is not true. Okay, unfortunately, that's not the curve here. Okay. Okay, so what is the functional here to be minimized? So what is the minimized thing? When a chain is hanging, the only physics or only force acting on it is potential energy. So you just write down the potential energy. Potential energy. So you write down the potential energy functional. That's all. You can compute any points. You put the coordinates appropriately, and the potential energy is happen to be mgh. You can normalize it if you want. The potential energy is integral a to b and y of x square root of 1 plus y prime of x square. So you, for a small place, you compute it and then you write down this. Okay, so this is your Lx, L of yx, y prime of x. I just changed the notation. That's a L of yx, y prime of x. Okay, and what is your LXQ basically? If you want this notation, LXQ is equal to x into square root of 1 plus q square. I told you the q comes as a velocity most of the time. So you want to find answer. So you want to solve y bar such that j of y bar is equal to minimum of j of y over smooth curves. Okay. So the exercise is again write down Euler-Lagrange equations, write down Euler-Lagrange equations and then solve it. And then solving, you get your yx to be cos hyperbolic, some constant cos hyperbolic. So it is not cos hyperbolic, okay. Cos hyperbolic of x over c, where c positive. I will leave all these are all exercises. Okay, so I'll stop here. So you see three special cases. One is the Newtonian mechanics, and then you have seen a problem from Brachistochrone, and then a third problem from the catenary. And you can actually, of course, initially the solutions are given by their methods, individual methods, but now you have a very general theory using Euler-Lagrange equations, and then if you can solve with that second order equation, you get the solutions to this problem. So I will stop here and we will continue little more about deriving, converting into a system of 2n equation. So we start introducing the Hamilton's ODE and eventually Hamilton's ODE, and then how do you introduce the Hamiltonian and Legendre transformations. So let me stop here.